Hi, I'm Veser, and I lead the Catalytic Reaction Engineering and Process Intensification Group at the University of Pittsburgh. In this brief video, I would like to give you a little bit of flavor of who we are and what kind of research we do. We are a diverse group of students and researchers currently comprised of one postdoc, 7 PhD, and 2 master students from 8 countries across 4 continents, including China, India, and Pakistan, Oman and Rwanda, Turkey and Germany, all the way back to the US. Our research focuses broadly on reaction engineering across all length scales, from atomistic level understanding of catalytic reactions to the design of novel intensified reactor and process schemes. I will try to use one brief example from our recent or ongoing research to illustrate each of these 3 pillars of our research. First, we are interested in exploring and exploiting nanoscale effects to tailor the reactivity of catalysts and other functional nanomaterials. In this example, we're designing what we call silica nanobubbles, that is, hollow, porous silica shells that contain highly stable and active metal nanoclusters in order to use them effectively as what we will call nanoreactors. We can synthesize these structures with near nanometer precision, and we were able to show that the nanostructuring of these shells allows us to selectively convert reactants in a reaction mixture. Here we are looking at the oxidation of a hydrogen-methane mixture. In the left graph, you can see that over a conventional nickel catalyst, hydrogen and methane are converted at similar rates, as indicated by the identical steep increase in conversion. If we instead use a nickel silica nanobubble at otherwise identical conditions, as shown in the right-hand graph, the conversion of methane is now significantly delayed. That is, we can introduce selectivity in the catalytic reaction without any changes in the chemical composition of the catalyst itself, purely by nanostructuring the material. In order to get insights into reaction mechanisms or capture high accuracy reaction kinetics, we design and build our own laboratory tools, such as special kinetic reactors, or use any of the many state-of-the-art facilities that we have available on campus at Pitt. Here, for example, we use Pitt's Environmental Transmission Electron Microscope in collaboration with Professor Judy Yang and Dr. Stephen House in our department to investigate the partial oxidation of methanol over a copper catalyst. This allowed us to observe the reaction dynamics in situ with atomic resolution as we reduce a copper oxide nanoparticle sitting on a metallic copper substrate with methanol. And we find, interestingly, that the particle radius of this copper oxide nanoparticles initially shrinks rapidly during the reduction, while the height of the particle remains unchanged. However, once the radius and height have identical dimensions, a second isotropic phase of the reduction sets in, which we are able to further explain via detailed theoretical investigations of the reaction mechanism. Finally, on the reactor and process level, we are investigating a range of so-called process intensification strategies. Process intensification is an emerging trend in the chemical industry to rethink existing operation schemes into ones that are both more precise and efficient than existing ones, as per the DOE's definition. I like to think of it simply as the reaction engineer's response to the challenge to develop a more sustainable chemical industry, doing more with less waste, less energy, less pollution. In one example, we are working very closely with a wonderful industrial partner in order to intensify the production of dispersants. The focus is on transitioning these processes from conventional batch processing to more efficient continuous production. We developed a systematic methodology for this process, starting with kinetics experiments in both batch and continuous laboratory reactors to derive robust reaction kinetics, embed these into detailed computational fluid dynamics simulations, implement these into full process models, and then use these models to scale up to pilot scale. Our industrial partner then built the pilot skid, which operated so successfully that it was immediately moved to a production site and put into full-scale commercial operation. We hence moved the entire process in less than 2 years from benchtop concepts to full industrial operation, with a reduction in capital cost and physical footprint of the plant by more than an order of magnitude, more than 30% reduction in energy intensity, and complete elimination of several waste streams. All of our work could, of course, not be done just by us alone. We are collaborating broadly with many colleagues in our department, the Department of Chemistry, Civil and Environmental Engineering, Material Science and Mechanical Engineering, and even the law school at Pitt. And we have numerous collaborations with other universities, national labs, and industrial partners as well. So where do our graduates go? Well, maybe the question should rather be, where do they not go? Students in my group get an exceptionally broad training as reaction engineers and are hence employed across many different sectors of the economy. The list here shows the employers of our graduates just over the last 10 years. It ranges from what one might call the classical chemicals industry, that is production of bulk and commodity chemicals, over specialty chemicals, the semiconductor industry, pharma and biotech, environmental assessment and consulting, and even banking. I hope that this brief presentation did whet your appetite for more. If so, don't hesitate to contact me with questions anytime by email.